Now we're going to take a look upward and backward and discuss the origin of the Earth and life. The birth of the universe involves both science and religion. Initially religion, ultimately science. About 13.77 billion years ago, plus or minus 40 million years, the universe went through the Big Bang. The universe has been expanding since that time, the time of the Big Bang. In an article from this summer, we can see that astronomers have used the oldest surviving light. This is light left over from near the beginning of the universe to place an age on the universe, to refine our estimate of how old the universe is. This is a portion of the Atacama Cosmology Telescope's image of cosmic microwave background radiation. This is radiation at about a 2 millimeter wavelength that was initiated at the beginning of the universe, or near the beginning of the universe. So this flash of radiation from just after the Big Bang has now cooled to 3 degrees above absolute zero, and with this cooling comes an increase in wavelength. So we're now at this 2 millimeter wavelength, which is microwave radiation. Some of the original photons from this Big Bang are still around, and you can see them on a TV if you have an old CRT TV by setting the TV to a channel that isn't functional and turn the brightness down until you can only barely see some little flashes on the screen. About 1% of those little flashes that you'll see on the screen are some of these original or primordial photons. And the rest is going to be communication microwave noise that we generate ourselves. Now, the reason we put these telescopes up high into the atmosphere is to avoid this. We've seen this kind of figure before. These are absorption spectra, in this case for microwave radiation. And this is as measured in Mauna Kea in Hawaii. So even at very high altitudes, we're still losing significant portions of this microwave band. We have to account for that when looking at the microwave background radiation in the universe, which is why we put our telescopes so high up into the atmosphere or in space. Following the Big Bang, we have a very orderly progression that includes the transition from strictly energy in the universe to energy and matter in the universe. The proportion of hydrogen and helium are correct as predicted by physics, and also inescapable in this lineage is the formation of stars and the formation of heavier elements within these stars. Ultimately, they're dispersed to outer space during supernova explosions, which we'll get to in a few minutes. This results in the formation of more stars and the formation of planetary systems, including planets like the planet Earth. Given a planet like Earth, it's impossible to prevent life from evolving. The Earth is the right size, the right distance from the sun so that it's heated by the sun, but doesn't have its atmosphere and oceans boiled off by the sun. That's important. And it's been given enough time for chemicals to organize into ultimately life forms. So through a series of steps, which we consider both logical and probable, we end up with intelligent life. Now, when you look at the natural world with fresh eyes, it's essentially impossible to imagine how all of this variety, all the crazy things that happen in the biological world could happen through a series of abiological steps, abiological transitions. So if you just drop somebody into a rainforest and ask them to explain how things got to be like this, the easiest way to explain it is, well, it was created by a creator, not a slow evolutionary process. So this would seem quite amazing if we dropped someone off at a coral reef. They would experience the same amazement. If you handed somebody a cell phone, an iPhone 12, or showed them an image of Starman cruising past the planet Earth here, these would seem illogical and unbelievable. If you take an iPhone apart and look inside, there's no way any human could ever understand that. How did this car get into space? There's no way any human could ever understand that. We've only been flying airplanes since 1903. It's only a little over 100 years we've gone from getting off the ground to launching an electric vehicle towards the sun. I guess it just cruised past Mars recently. Out of this primordial need to explain the existence of our world has come religion in all of its multifaceted, often contradictory, and even absurd manifestations. This was a statement made by Cesare Emiliani. He's famous for discovering that there were not 4 ice ages, but more like 20, and a bunch of other important discoveries. If we look at the world through time, everything seems to have evolved necessarily and inevitably from simple to complex, from primeval fireball to our modern civilization. Unfortunately, no one was around to record what had happened in the past, at least not until the Egyptians and the Babylonians, when they first started writing things down. Observations were written down, and those records persist to this day. So, of course, one of the early questions is, how did we get here? How did this world come about? Why am I in Saskatoon? According to the Old Testament, God made everything as follows. This is also, to some degree, in the Quran and the Torah, in this order. A little worded differently, but it's been translated to lots of different languages. On the first day, we have separation of day from night. Day 2, the sky separating the water below from that above. On day 3, water under the sky gathers into a basin, the ocean basins, letting dry land emerge, so we have the appearance of the earth. Trees appear on land with fruits and seeds. On day 4, the sun, moon, and stars appear. Day 5, marine animals and birds. Day 6, wild animals, cattle, reptiles, man, and woman appear. On day 7, a day of rest after all of this work, and the Simpsons and NFL. So the Jews make the world in a simple, more or less logical way, a readily graspable amount of time, a week. The Greeks, though, had a different way of looking at things. The Greeks made things so crazy, so many gods doing so many crazy things with and to other gods, that eventually they started to become suspicious. This stuff can't be true. And once people started questioning the Greek religion and the characters in the Greek religion, we have the birth of science, this questioning of things that people tell you. That doesn't seem correct. That seems impossible. Those kind of questions become the basis for scientific thought. And this is evolving in lots of institutions around the world. And it's been evolving ever since we came up with the ideas of science as conflicting theory to that proposed by religion. About 6 years ago, Pope Francis declared evolution and the Big Bang Theory are real, and that God isn't a magician with a magic wand. He went on to say the Big Bang, which today we hold to be the origin of the world, does not contradict the intervention of the divine creator, but rather requires it. Evolution in nature is not inconsistent with the notion of creation, because evolution requires the creation of beings that evolve. P.F. Pope Francis. So he is saying that science and religion can coexist. Now, this is Stephen Hawking. He is responsible for a lot of our understanding of the universe, the origin and history of the universe. It is summarized in a movie called The Theory of Everything, which is based on a book called The Theory of Everything. So it's a little difficult reading, but it will give you an understanding of what's going on in the universe. Essentially a much, much longer version of what we're going to cover in the next hour or so here. So this brings us to cosmology, the oldest science that we're aware of, the oldest science that persists to this day. All civilizations, from the most ancient to the most modern, make and record observations of objects in the sky, their behavior, and some people do this very accurately. There were a few, like Tycho Brahe, who were oddballs. Here are a couple images of him. He was a wealthy Danish astronomer. He's famous for a couple things. One is this. He got into an argument, most likely or possibly a mathematical argument that resulted in a duel and the slicing off of his nose. So he had a nose made out of an alloy of silver and gold with a little bit of copper in it. We do know that for sure because the nose was recovered from his grave in 1901, and his skull was a little bit greenish. So he had a gold, silver, copper nose that he would pop onto his face. He carried glue around with him to glue it on. when needed. He also had a pet moose. And the reason he had a pet moose was reindeer didn't work out. The reindeer were too warm, had died from the heat. Moose that he had followed him around like a dog, drank beer with him. Unfortunately, the moose drank so much beer at a banquet that it fell down the stairs and broke its leg. And that was the end of his moose. He had a little person living under his desk that he would ask advice of. And anyway, you get the picture.
What a strange person.
He's also a very good scientist, though. So the positions of the planets were recorded against the backdrop of the stars. The stars never seemed to move. So they formed a grid to detect planetary motion. And it's this planetary motion that he was so good at modeling, so good at recording, and he developed his own instruments to do this. You could still see some of them on display in Beijing. Copies were made from the originals in Prague, and the ones in Beijing are still apparently functional. I haven't seen them myself. It was the interest in the motion of the planets that first led people to think that these bodies determine human events. If planets are in some particular alignment and my geese fly away, maybe my geese flew away because the planets were in that alignment. If a comet appears at the same time as a plague, maybe that comet caused the plague. Things like that. So this ancient astronomy in reality was more like astrology. People were interested in what was going on in space because of its potential influence on their lives. That being said, how did we get here? Well, we need a time machine, and unlike Dr. Evil's time machine, we merely have to go outside and look up. When you look up in the sky at night, you're seeing back in time, and you're seeing back in time to varying degrees, seconds to billions of years in some cases. This is the Hubble telescope's deepest view of the universe, and we can look nearly back to the beginning of time in images like these. This is the 10,000 galaxies in the Hubble Ultra Deep Field. This image includes galaxies of various ages, sizes, shapes, and colors. The smallest, reddest galaxies, like this one, maybe this one, maybe that one. Well, you can go through here. There's about 100 of them. Might be the most distant known objects that we can observe. And these were present when the universe was 800 million years old. So about 13 billion years ago. So that tiny red dot is looking back 13 billion years. The nearest galaxies, the big spiral and elliptical galaxies like these, are about 1 billion years old. These images that we see happened 1 billion years ago when the universe was only 13 billion years old. This is a great image here. You have the Hubble telescope sitting here in the modern world. And the further back it sees, the further back in time we're traveling. So here we're at 13.77 billion years since the beginning of time. The Hubble Deep Field represents time about 1 billion years after the universe was created. The Hubble Ultra Deep Field represents a period of time in the universe's history when the universe was about 400 million to 700 million years old. And we see evidence going back further to the appearance of the first stars, somewhere around here. How and when did this universe come into existence? We know now, we're constantly refining this age, that the universe began about 13.8 billion years ago. Exactly how it happened is a little bit more difficult. The universe is now expanding. If it closed, if its density becomes greater than 6.5 times 10 to the minus 30 grams per centimeter cubed, we don't know this answer yet. It will slow down in its expansion and then collapse about 100 billion years later. So you can think of the universe as kind of an organism breathing in and breathing out, breathe in, breathe out. And under this model, the universe is going to expand, slow the expansion, stop, collapse, crunch down to a singularity, and then blow up again in the next Big Bang. So when these particles collapse into a singularity, we're talking about a point of extremely high, perhaps infinite density, and extremely high, perhaps infinite temperature. So here we have material entering a black hole and ultimately becoming a singularity. Black holes can potentially come together, multiple black holes join each other, and maybe eventually the entire universe will crunch down again into one of these singularities. So space itself collapses in that point, and within that point, matter and energy are indistinguishable. The point contains all the matter and all the energy of the universe, around which there is no space and no time passes, which is kind of cool. There's no space, there's no time. Everything is together in an indistinguishable, tiny point. How long did the singularity last? Well, if you listen to Groucho Marx, time flies like an arrow, fruit flies like a banana. I guess that doesn't apply here. The question is meaningless. If time does not flow, an eternity or an instant, no time at all, is all the same. What does seem critical, though, is that this situation isn't stable and has to change. And how does it change? It becomes the universe. For the first 3 times 10 to the minus 10 seconds, the temperature was too high for matter to be stable. Only radiation was stable, and therefore only radiation was present. This first period of time is known as the Plankian. The Plankian is defined by the time it took light to travel the Planck length. The Planck length is 1.616 times 10 to the minus 35th meters. It's a very tiny distance, and it's a very tiny distance that light travels, which means it's a very short period of time. This is considered a God unit because it's a natural unit of time. A second is something that we as humans develop. This amount of time, the time it takes light to travel in a vacuum, this distance is not related to humans in any way. It's completely natural, therefore it's called a God unit. We didn't make it up. Well, we sort of did. Because we don't know if our fundamental constants operated during this period, nothing is known about the Plankian. So we have ideas, lots of ideas, but if physics doesn't operate in a way that we can observe today, we are a bit lost. We're hanging out there waving in the breeze. This Plankian, which lasted about 5.39 times 10 to the minus 44th seconds, was followed by the Gamawian. This Gamawian is the second eon of cosmic time, and we know quite a bit about it. This Gamawian ranges from the end of the Plankian to 4.6 billion years ago. This is when the solar system formed. It's the longest eon in cosmic time. Since the beginning of time, the universe has been expanding. The rate of expansion has either been increasing, constant, or decreasing. You can hear somebody outside decreasing, backing up, beeping, the constant beep. An increasing or constant rate of expansion leads to an open universe, a universe that will keep expanding forever. A decreasing rate may lead to a finite radius, also called a flat universe, or it may decrease to zero and then reverse itself. In this case, the universe is closed and will eventually collapse back into another singularity. Expansion involves the continuous creation of space between celestial objects that are not sufficiently bound to each other gravitationally, namely galactic clusters. So not everything in the universe is moving away from everything else when we talk about expansion. It's galactic clusters that are moving away from each other. The space between galactic clusters is increasing with time, not the distance between one galaxy and the next, or the distance between stars within a galaxy. So we're getting closer to some stars, getting further from others. For the most part, we're getting further from other stars. During the earliest Gamawian, the 4 forces of nature were part of a single superforce. In order for this to make sense, consider gravity to be the weakest of the 4 forces of nature. The mass of a particle increases with increasing speed, such that the mass of even the smallest particle would reach infinity if the particle could be accelerated to the speed of light. At very high temperatures, 10 to the 31st Kelvin, prevailing at this time, T is equal to 10 to the minus 43rd seconds. The mass of particles was so large because of their speed that the gravitational force between particles was as strong as the strong force. So we're getting into some really heavy-duty physics here, where particles are incredibly massive because they're moving very fast. The other 2 forces, the electromagnetic and the weak force, which are intermediate in strength between gravity and the strong force, come about next. As a result, above 10 to the 31st kelvins, the four forces are indistinguishable. As the universe expands, temperatures decrease. And this causes the mass of the particles to decrease and gravitational interaction to weaken. Therefore, gravity is the first force to appear as a separate force. The next force to separate was the strong force, followed by the electroweak force, which quickly split into the electromagnetic force and the weak force.